Okay, good afternoon everyone and welcome to EET 2256. For those who haven't had me before, my name's Dr. Glenn Matthews and I'm the course coordinator for 2256 this semester. I'm also looking after Computing 1 and now the program manager for BH072. So, what are we going to talk about in 2256? A couple of things. What I want to do today is give you a brief overview of what the course is going to entail. I'm going to show you on Canvas where you'll find the various bits and pieces that we need to get through the course. We'll introduce some of the hardware, so some of the microprocessor platforms we'll be dealing with. I've got a couple of examples of things we've done here. And then if we get time, hopefully we will, we'll actually start our first embedded project and we'll actually write some code that we can later on in the semester deploy onto our target hardware. Okay, that's the aim of how today will hopefully go. Okay. So what's this course all about? And the aim of this course is to give you the necessary skills that you're going to need as soon-to-be professional engineers to actually develop hardware and software solutions that run on these guys, that run on embedded systems. It is very, very different to... Everyone's done 2246 or Computing 1? Okay. A few of you, hopefully most of you have done that. If not, it's not a big deal. But we're writing software or firmware that runs on these platforms, on embedded systems. Okay? So not on the PC. And that's a very, very different process than writing applications that run on our computer. Many of the problems that we're going to come across are things that I've had to do before. They're real-world problems. Okay? To give you context, I work with defence on their radar systems for their drones. Okay? I also work with a large German company on some of their hardware and software solutions, as well as a few companies within Australia. So these are examples or cut-down examples of platforms that we've had to develop before. And by the end of the course, you should be able to write firmware or code, okay, software, for embedded systems to perform certain tasks, certain operations that we want to do, both in C, okay, we've all seen C before, hopefully, and definitely in assembler, another programming language. That's a lot closer to the hardware than you generally have seen before. So we're going to actually cover both assembler and C in this course, okay, or aspects of both. And it sounds a lot learning two programming languages. It's really not that bad. You'll be required to develop interfaces, okay? So connectivity from outside devices. It might be a keypad, it might be a keyboard off a PC, it might be a piezo distance sensor, that sort of things. Those sorts of things, rather. And communicate whatever they're reading back into our embedded piece of hardware. Okay, so getting real-world data and applying it on our technology. And then one of the other really key aspects of this is to look at commercial data sheets produced by Atmel, in the case of Microchip these days, ARM, those sorts of things, data sheets for chip manufacturers, sensor manufacturers, being able to interpret them and being able to actually understand what it means and how do I use this device. Okay? I'm going to move more away from the theory aspects. I want to get more onto how do we actually build this target hardware, what can we build here, what do we send overseas to be built. Okay? Now, how do we assess all of this? There are individual labs for this course. It has changed since last year and I'll discuss the changes. Individual labs which account for 18% of the overall subject. Okay? As it says, the tasks are to be completed individually. Last year they were grouped, this year they're individual. And that was based on the CES. The results, or the comments that we had. There's 3 core labs with different weightings. So lab 1, or I'm calling them lab tasks 1, 2 and 3, are 5, 6 and 7% respectively. They get more difficult as we move through the semester. Generally, well actually they are 2 weeks per lab. So labs start next week, week 2. So you hopefully start that lab over the weekend or tonight. Lab 2, you do start in week 2 and then you submit it in week 3, okay? And then what remains of week 3, you start lab 2 and so on. So it's a 2-week cycle on those core labs. You are required to submit your code for those labs but the marking for those actually occurs in your laboratory session. So we don't have formal reports for these. As I said, I'm much more interested in your ability to drive the hardware than the documentation on how you've actually done it, okay? That's really important. Now, equally, what we're going to have is there's going to be a couple of tutorial quizzes held throughout the semester, okay? And you need to submit your lab code, the entire Atnol Studio project, zip it up. Zip files are the only ones accepted, not 7-zip, .zip. They must be submitted to Canvas by the due date or time, otherwise there's an automatic 30% reduction in the grade. Okay? So please make sure you do submit that code. It's really, really important. All right. Then as we move to the second part of the semester, there's going to be a group project, so maximum of 2. You can work on the project individually. I have no problems with that, but I can't scale the assessment, okay? So just be aware that if you decide to work on it by yourself, it's still the same amount of workload, okay? But that's fine. That's up to you guys. Also, I'll get to the group part in a second, and that's worth 30% of the overall subject grade, that group project. We split it into 2 components. There's a presentation in week 8 where you're going to present to your class how you think you're going to solve the problem, okay? Some ideas and some concepts. And then in week 11, the final assessment, which involves a demonstration to your lab tutor of whatever you develop and a report to go with it, okay? Demos are assessed in the class with your tutor. Reports are assessed out of class by the tutors, okay? And as I said, for the majority of the assessments are done in the lab, so it makes it a lot easier. Now, in 2019, what we're going to do is we're going to create a project or create some hardware that interfaces with our board that uses one of the standard interfaces. So, you know, some of the more advanced ones are called I2C, UART, SPI, those sorts of things, and we'll discuss what they mean throughout the semester. Last year, some of the projects we had an ultrasonic rangefinder. So part of it was we had some students work on these boards, we connected the ultrasonic rangefinder, and then depending on the location from a wall or from an object, the LEDs would light up. So the closer you were, the more LEDs lit up and so on, okay? That's a pretty simplistic project to achieve, but they got a lot more complex. Now, what I'm actually most likely going to be doing with these projects is weighting the projects. That means that there will be, the topic list will come out, and you'll see that there's, if you do this project, everything's perfect with this project, the maximum grade you can get is a pass, okay? And then there'll be another one for a credit level project, distinction and high distinction level project. The reason being is you can pick a project that you think you're capable of achieving, okay? The pass level, credit level project will be a lot simpler, but be forewarned that if you do a pass level project and don't spend the time on it, you do put your grade in jeopardy for passing the course, okay? So just keep that in mind. I'm going to release the major project details a little bit later in the semester. I don't want to overwhelm you with too much information, but they will be released before mid-semester break, so you can at least go through all of that content prior. Most likely week 5, I'll release the project details. Now, this year we're running classroom tutorials, so there'll be a 1-hour tutorial per week in a lab, okay, where you've got physical access to computers, okay, right? Probably just a simulator, not the real hardware. But they'll be to support the labs. So there'll be to things like exercises in using assembler, okay? Problem-solving projects, more of like workshop-style tutorials. So some might be in groups, some might be yourself, problem-solving exercises and those sorts of things. If anyone's ever seen the inside of my office, you'll see there's electronics and stuff everywhere. It's an absolute mess. Can't find any paperwork. I like doing this stuff. I'm an embedded engineer by trade. So I want the assessments to reflect that. I want them to be problems that you have to solve rather than some theoretical aspect of the course. Okay? Also, in the tutorials, 3 tute quizzes, 5% for one and 2% for the other 2. Most likely we'll run them via Canvas. I've just got to find a nice way of doing that. And that's going to be based around all of the content that we cover in lectures, tutes and labs. It's not going to be some obscure footnote in a data sheet somewhere that only 5% of people have come across, okay? The information that you'll need will have gone through. And the first shoot, which starts on Monday, is going to introduce the development environment, the IDE, at Mel Studio that we're going to use throughout the course, okay? Now, other things, there is a final written exam at the end of the semester, and that's worth 35% of the overall subject. Now, that's going to, again, cover the same sort of material. It's closed book, and it's going to require you to write assembler code or C code or a combination of the two, interpret it, find out what's wrong with a piece of code based on the embedded hardware or the platform that we use throughout the semester. So it's vitally important that you actually learn to drive the tools, learn to drive the hardware, and not just watch what's going on. Okay, it's really important that you're actually working with the real hardware. So in terms of course activities, what have we got? You've got a 1 by 2 hour lecture with me, weeks 1 through to 12. There's a 1 by 2 hour lab session, so weeks 2 to 11, inclusive. Now, excuse me, you guys aren't in first year anymore, okay? So what we want you to do is experiment a little bit. We want you to, use the oscilloscopes, use the debug hardware that we've got. If things aren't working, it's not, oh, it doesn't work and walk away. It's, well, how do we debug it? That's what part of this is about, okay? How do we use all the support tools that we have to work out what's happening in these embedded systems? And as we'll find out, debugging hardware can become quite complicated, okay? On a PC, we can set a breakpoint, we can stop at a point, see what's going on. On an embedded system, it's very, very different. There's different ways of debugging it, different techniques we need to work with. And hopefully we'll get through to some of that. There's as I said, a 1 hour tutorial per week, weeks 2 to 11. And as we need it, I can produce some additional video content or find some relevant YouTube videos or whatever and add that in as well. Okay? Now, the lectures, most of you would have been in lectures with myself before. The way they normally sort of work is we might explain some of the key principles, go through some of the technology, what we need to know, and then actually cut code. We'll actually sit here in the simulator, and if we need to, with the actual hardware, and actually start doing demos in real time. So if you've got your own laptop or device, whatever you've got, bring it along, code along with me, not a problem in the world. Ask questions. I want these sessions to certainly be interactive. Okay? Any questions about the assessment so far? Seems pretty clear? Yep. Yes?
Do we know what weeks the quizzes are going to be?
I haven't done that yet. The reason being I want to see how everyone's travelling. But as soon as I know, I'll definitely give you a week's notice. I'm not going to spring it on you and say, oh, guess what, guys, this week you got a lecture. I'll at least give you a week's notice beforehand. Yep. Yes? No, we're using another tool called Mel Studio. I'm going to show you that today. Yep. It's based on Visual Studio, actually. Any other questions before? Yeah.
Is the final written exam, is that just going to be like literally written, not actually on a computer?
Yeah, unfortunately, I've begged my deputy head, Alan T, to give me 300 computers out at showgrounds. I can't get them. I'd love to be able to, but I can't. Maybe next year. If anyone has been through this course before, it is definitely a different format. Last year, it was a 1 hour lecture, then you go and watch some videos, and then it was 4 hours of labs. I've completely scrapped it, okay? So just be aware that there are a lot of changes in this course. And the other thing is that I am rewriting this as we go. I wasn't happy with it last year. I shared it with somebody else. So I do apologise in advance if things are coming out right on deadlines, or lecture notes are coming out the day before. I'm desperately trying to get it done, and I'm running 2246 and 56. So just keep that in mind. Staffing, okay. So lectures are based on electronic resources where I can, as much as I can. And you'll see in the lecture notes, the last slide has a list of references that I've used to generate those slides, okay? Usually it's based on, there's one textbook that I'm using in particular, and usually the data sheets for the chips are enough for this particular thing, which are all, the data sheets are certainly available. But I'm not expecting you to go and buy the book, all right? If you need content, I will provide that content, okay? And because of the architecture we're using, there's a lot of information out there. And if we need extra material, I'll point you to it. It's certainly not an issue. I am basing some of the examples on that because they are sort of fundamentals examples as well. And as I said, I'm delivering the whole lot this year. Course coordinator, lecturer, you name it. Any issues, any course administrative issues come to me. I don't have any control of the timetable, okay? And we're running pretty much at quota. We've pretty much got all the labs full. So if you have an issue with a clash that you can't resolve, please contact student timetabling. There's absolutely nothing I can do, okay? So give them a yell and hopefully they can solve any issues that you may have. What you will find though, people drop out, all right, so labs become available and you might be able to shuffle yourself around as necessary, okay? And then I have about 5 tutors assisting with this course, and their details are going to go up on Canvas. They've just been employed. Sessional contracts have just gone out today. And once they're all accepted, they'll pop their details up. So you know, for the photo, you know who your tutors are, you know their email addresses. I'll show you where that lives on Canvas. And unfortunately, they're only available during lab classes. Anything beyond that, myself. Now, what I will say is that I have 725 students I'm looking after this semester. Send me an email. I'll do my best to get back to you in a timely manner. If I don't, come and see me. All right? I'm not being rude. There's just too much going on, okay? My office is 10707. All right? Just come and see me. Don't ring me. Come and see me, okay? Best, because generally what I'll do is I'll book you an appointment then and there and try and solve that problem, okay? Equally, I'm more than happy to spend half an hour at the end of the lecture outside answering questions. Not a problem, okay? Technically, I'm running a help session for 2246, computing 1, 4:30 to 5:30. Actually, I can't be out here at the end of that because I've got the help session. Come to the help session for 2246 and I'll squeeze you in there. I'll do my best. That's going to be in 10/9/13 from week 2 from 4:30 to 5:30 of a Friday. I'm sorry it's Friday at 5:30. Best I could do to try and get everybody to fit in that room. Okay? So that'll be there as well. But if I don't get back to you and it's super urgent, just come and see me. It's not a big deal. Okay? Now, just trying to get hold of me, and this is in general. Canvas gives you all these great tools to communicate with people, but it doesn't tell me what goes on. One of the problems I have is if you put a comment in an assessment or discussion boards or things like that, I don't see it. I don't get notified that something's happened. Okay? So, best thing to do, use your student email address. We're not allowed to reply to private Gmail addresses, okay, or whatever other mail client you've got, mail service you've got. Send me an email with 2256 and your student number in the subject line, and I'll do my best to get back to you in a timely manner, okay? Canvas. Has anyone seen this little box on Canvas before? The one here that's on your grades page. Now, we've had a few issues with this in semester 1. I'll show you where it is. Canvas by default calculates your final grade only based on what you've submitted. Okay? If you don't submit something, it ignores it. So your average grade will be less. We've had cases of people saying, hang on, I got 85 and I got my transcript and I failed the course, what's going on? Because you only submitted one thing. You got 85% for the one thing that you submitted. Okay? You need to make sure that that's turned off when you're looking at your assessments. Otherwise, you may get a shock at the end of semester. Okay? Course outcomes. So by the end of the course, and I promise we'll do our best to get to some actual hardware today, what should you be able to do? And this is taken out of the course guide. You should be able to interpret a microcontroller instruction set and actually understand how those instructions are performed in the architecture. Okay? How does the data move from this point to this point, and how does it do something with it? And we're going to be using what we call an 8-bit processor, and we'll explain that shortly. Design, test, and evaluate embedded systems and the solutions that we apply to real world. Okay? So we think about embedded systems, they're everywhere. Okay? We've got to be able to evaluate these and know whether they're actually suitable for their purpose. All right? As engineers, that's what we need to be able to do. You should be able to look at these systems and decide, okay, what features do I need to perform a particular task? What's important? Why would I pick that over an ARM processor or something else? And I'll show you an example of those shortly. You should be able to develop develop software systems for embedded devices using assembler C and C++. We don't really do the C++ side, but we certainly do assembler and C. If you haven't done C before, don't worry. Some students are doing 2246, computing 1 and 56 concurrently. That's fine. Some people have never seen C before. Don't worry about it. Okay? We'll guide you through that process. If you're worried about it, come and talk to me, and then we can give you a few more hints and tips. And you should, most importantly, design, test, and evaluate embedded solutions to real-world situations. And these systems will be interfaced to real hardware and interpret that. And as we said, the whole idea is this course is I've got a really strong practical emphasis. I like embedded. I want you guys to like it as well. I want you to be able to work with it and not be concerned about, you know, something going wrong with it and what happens if something goes wrong, and being able to deal with it. So, you know, what we're using is we're using an open source platform. We're using the OUSB board, okay? That means the reason behind that is you can purchase it if you want. Okay, there's no issues. There's full class sets. You don't have to go and buy it. But if you do want to work outside of class, it's handy to have one, okay? If you've got one from existing courses, we can reflash it, we can put new software on it, and it will work for you. If you've got a second-hand one, we can check it over, we can make sure that it works. If you want to use the class sets, that's fine, but they are certainly only available in your actual scheduled lab. Okay? So that's what we're going to be doing.
Where would we go if we do have one that's maybe
Yep, sure. So what I'll do is I'll attempt to break this one today, and I'll show you how to reflash it. Yep, we'll try and get through that today if we've got time. If not, I'll point you to where to go. Now, I don't really want to do this slide, but I have to. Okay? Just remember that what plagiarism is. This course is predominantly, apart from the major project, individual assessment. And just be reminded that, you know, plagiarism is not tolerated at the university. I've got 7 hearings to go to next week, and I don't want to go to them. Okay? We don't want this to happen. I don't see this being a problem in this course, but just be aware the work is individual. Okay? You submit your code electronically. That means I have everybody's code. So don't copy code. Just don't do it. All right? It is a serious offence, and it can, at the worst case, actually mean you're actually suspended from the university. Okay, put your university career on hold, and if it's repeat, it means that you can be removed from the university. So we don't want this to happen, okay? Unfortunately, I have to go through these because unless we do, I get in trouble. Also, the same thing with enabling plagiarism, okay? I am more than happy for you guys to sit together, discuss ideas, concepts, whatever you've got, okay? That's what this is about. If anyone knows my office, I sit next to Samuel. My office is next to Dr. Samuel Ippolito. He and I are constantly at each other, planning ideas, working things out, okay? That's what this being an engineer is about. Do that, not a problem. But just don't hand over solutions, don't hand over flash drives with code, and so on. Now, just some examples. Just so you know, we'll call it Bob, okay? Bob has a friend in 3rd year, has completed this course, got a HD. Bob asks his or her colleague, can I have the work so I can submit it? Okay? Both Bob and his friend are done for plagiarism. Okay? Because enabling plagiarism is treated the same as you submitting someone else's work. Okay? And there's a few other examples there, so please just don't do it. This one we see, the bottom one we see all the time. Someone approaches you and says, I'm struggling for lab 3, it's going to be marked tomorrow. Can I just have a look at your code and modify it? And I modify it enough that it won't be caught. Come on, it'll be caught, okay? Don't do it, all right? Let's move on from that. So, let's go to Canvas. So, which course are we at? This one. 2256. Now, under syllabus, what you'll see is the topics that we're going to cover this semester. These are suggested topics. I'm going to do my best to get through all of them. I will get through all of them in some way, but the week numbers may shuffle a bit just depending on how we're progressing. If we're finding we need to spend more time somewhere else, we will certainly do that as necessary. Some of the lectures have are split into half, so an hour each or so on, but you can see the syllabus, what we're going to go through, and hopefully we'll get a couple of examples out today. We'll look at the AVR, so the OUSB board and its controller. We'll do some assembler level stuff. Then we'll move on to C. How do we interface real hardware? How do we plug things into this and make it work? Serial comms. So how do we make this board talk to something else? Communicate with something else. We cover that. Timing and counting, always important. Data conversion, analog to digital conversion, those sorts of things. Then we'll get into some of the more tricky stuff, the stack and subroutines, interrupts. So an interrupt is where we can say, hey, stop what you're doing, this is more important, go and do that, and then it returns and comes back. We're going to look at that as well. And that's really important for timing critical things. Okay? And if we get the chance, or when we get the chance, we'll do a revision in week 12. Okay? The dates here are week 1 commencing Monday the 22nd of July. So just so you know what those dates actually mean, they're not the lecture dates. So, and then what you'll see is the labs on the right-hand column. So lab 1, basic assembler, and then in week 3, you'll do the demo for that particular one, and so on. Now that, if you finish the demo, let's say you finish it 20 minutes into the 2-hour lab, I would highly recommend starting the next lab, okay? You need all the time that you can get for this course, and you can certainly start it in advance. That's why I've released the first 2 labs. They're all ready to go. You can see the content, okay? So you can certainly do that. So we do some assembler here. We do some algorithm stuff here. We interface with a matrix keypad, like an alarm panel style keypad. Then we get into the project, and you can see that the project runs over roughly 4 weeks. You can certainly start it early if you need to. So that's the breakdown of how the semester is going to work and the assessment weightings that you see here. Okay, move on. Course orientation, that's my ugly mug, we don't need to deal with that. Course guides, really, really important. Has anyone actually read the course guide for this course? Had a look? Okay, couple of important things. There's my contact details. Prereqs, so what I'm expecting people to have done. If you haven't done these prerequisites, I can certainly point you to do additional material that can help you along the way. But I come into this course writing content knowing that this is what I'm expecting. CLOs. The assessment task weightings, so what each assessment task is worth. Now the interesting, or the important part, is if you go to part B, or this part. Has anyone actually ever looked at these 2 very important pieces of information? What they mean is that you'll have 54 contact hours with myself and the sessional staff. So 2-hour lecture, 2-hour lab, hour tute. Okay, taking into account weeks 2 to 11. And then I'm expecting you guys to spend 58 hours per semester to get a passing grade. That means pass. Okay? It's going to take more time than that to go higher than a pass. Now this is standard across the uni. 108 hours, roughly 104 to 108 hours for every 12 credit point course. Okay? 4 12 credit point subjects, 36-hour work week. That's how it works. Okay? Now, that's not, I'm certainly not saying you can't work outside of uni, you can't have a break. You have to, right? But just keep in mind that that's a time expectation. All right? It's a couple of hours here or there a week. Brings that up really quite easily, and I've designed the labs for that. You won't get the labs complete by just turning up for that 2-hour session. You have to do the work outside of it as well. Some more contact details. This is the actual book that I'm using, this second one here, but I'll put details in as necessary, notes in as necessary as we go. The assessments again, and group work. Okay. just make sure you read the paragraph on group work. You don't have to read it now, but group dynamics are always a problem. No matter which course you're in, you always get someone in the group doing more work than the other or so on. Make sure you read that. If there's any issues with your group partner for the major project, I need to know, your lab demonstrator needs to know, and we do our best to try and sort it out. Okay? So just be aware of that. And we, or me, as course coordinator, may actually decide to weight the assessments different for each member in the group depending on their contribution. Okay? And that's, again, that's true for a lot of our courses now. Back here, modules. Teaching team is myself, Jing's our lab demonstrator, and Shirish is one of our other lab demonstrators as well. Their contact details are up there. Get to know them, all right? And when it comes time for CES and all those surveys that we need to do, I'll point you back here so you know who your lab tutor is, because we get that question all the time. Course resources. Okay, so what do we need for this course? Now, if you haven't done C before, if you're a bit unsure, we've put a link up here to a free ebook, Teach Yourself C++ in 21 Days. Good revision if you haven't used it before, haven't used C before. The tool that we're going to be using is called Atmel Studio 7, downloadable from this link here. It's free, okay? You can put it on your laptop, you can put it on your desktop at home, whatever it may be. It's a Windows tool, okay? That's a Mac, but it's running Windows, all right? You've got to be running Windows for this course if you want to actually program the device, program the USB board, okay? There's a simulator as well, but yeah, run Windows, and that tool has been installed in all the labs, all the necessary labs, and it should be available on my desktop as well. The catch with my desktop is you can't connect hardware to my desktop, okay? So it's not a good solution for us, but it's at least there in terms of simulation. So grab a copy of that. It's quite big. It's about 900 odd meg. So use RMIT's network to download it, take it home and install it. Okay? And I've got this other package which I'll point to in a second. Now, as I said, how many people have got USB boards, just to get an idea? Okay, so quite a few of you. They can certainly be reused. There's not a problem with that. If you don't have one and you wish to buy one, as I said, it's not compulsory. You need to fill in this form here. The boards cost $70, and what happens is that they go into your voluntary fees, not refundable, so your next invoice you'll get charged at $70, which has to be paid, and you can use that board if you haven't done it for 2246 and 2250 if you're doing Samuel's course, the Advanced C course, okay? But equally, if you've got a second-hand one or you can scrounge one from a colleague who's in third year, not a problem. There's no significant changes. The only difference is we will most likely be phasing it out in the next 2 years, but we'll certainly be using it for this course. We're looking at updating the hardware to something a little more modern. But you fill that in, you take that form to Kiri, so the design store, Building 12, Level 9. You walk down into Building 12. You'll see Kiri's there on the left-hand side. He'll check it, and then he'll hand you a brand new OUSB board. There's about 200 new boards, 200 to 300 new boards. So if you want one, get it soon, because I've got 723 students that might want one. So get in early before they run out, okay? Because I'm using them in both courses. All right, so that's available there as well. RMIT resources, things like the library. How we use Canvas, that's cool. Here's a bit of background there. General course queries. We do have these discussion boards, but I don't really use them. I don't get notified. So just email me if you've got a problem, if there's any issues. If that's the case and everyone's having the same issue, let your lab demonstrator know. They pass it on to me or email me, let me know, and then I'll send out an announcement to everyone so everybody's got the same piece of correct information. Okay? That's the easiest way. So vital to this course is this particular page. the OUSB resources. What you're interested in is, there's two variants of the OUSB boards, and it explains the difference. We have the schematics, which is effectively the wiring of how this thing's on its printed circuit board. Grab that. Thank you. There's the full data sheets. You're going to need all of these data sheets. So grab a copy of these. These give you the information about how this chip, how this microcontroller actually works. Its internal structure, the instructions that we need to write software or firmware for it. So you will definitely need to know those. You definitely need to have those, rather. Okay? And there's also what we call some firmware. So if you've got an old version of the OUSB board, you can actually update the software on it so it will work in this course. If you're finding it's not working, we reflash it, re-put the software on it, and it's good to go again. Okay? Now, if you get super stuck and can't get it to work, come to the help session. I'll bring my programmer along with me and I'll reflash your board for you then and there. If not, if I'm not available, if you see Chris DeVos, Building 10, Level 9, Room 15, Chris with a K, K-R-I-S, he can reflash your board. If he's not busy, it can usually be done in about 5 minutes and you're good to go. Okay? So that's there as well. But there are tools that I'll show you in a second that allow us to reflash these boards. 10, 9, 15. So the labs, I published the first lab. This is worth 5% of the course. And what you'll see here is the lab guide and the sample project that you need to get started. Has anybody had a look at the lab guide yet? Anyone? No? Okay. So you can grab a copy of this. It's actually, you know what? I'll overwrite that one. The lab guides are fairly comprehensive. Okay. There's a lot of stuff here, all right? And you'll see that there's marks associated with each task. Okay, this is what your tutor assesses. This is where they come round and they grade you based on that criteria. It's a binary marking criteria. It works or it doesn't. Okay? So, if you don't get Section A complete, for example, or it's half working or intermittent, you won't get those 2 marks. You get 0 for that component. And you move on to the next component. Okay? That's how it works. So that's already published and certainly available. And this particular first lab is going to require you to write some code that looks through a table and finds the smallest number and its location in memory, the largest number and its location in memory. Okay? And you've got 2 weeks to do that, but we're doing it in assembler. And we'll go through how to start all this. It's not as bad as it seems. And some instructions and some background on how it actually works and so on. So that's all set up, ready to go. To have your work assessed, what I want everybody to do, and I had a meeting with the tutors today, the way this is going to work, this is during week 3. Okay? So what you do, go into your lab week 3 with it ready to be assessed. The tutor will give you a whiteboard marker, you pop your name up on the whiteboard. All right? What will happen is they'll then come around and start assessing people on the whiteboard, crossing names off as they go through. Okay? If you don't have it assessed in the time that they say, it gets 0. Right? So you've got to go in there with it ready to go. Okay? And then you can spend the remainder of time working on the next lab or asking questions or so on. And the tutors might change your code. They might get you to explain stuff. They will get you to explain stuff. And equally, make sure that you upload that code, otherwise that project, otherwise the 30% reduction will apply. We don't want that. So lab 2's there, sorry, lab 1's there. Equally, lab 2 is available, sorry, lab 2 becomes available, yeah, I might change that date, I might move it a little bit earlier. Lab 2's available, same deal, it looks the same. Let's go back. So lab 2 extends upon that and gets you to output some data to the LEDs or light emitting diodes. And again, you can see the same deal. There's a marking scheme and so on. Okay, so I'll change that release date so you've got that early on in the piece. Lab 1, you're actually using the simulator. When we write code for embedded systems, we don't go straight to the hardware as much as we want to. We actually do it in a simulator first, confirm that it works, then push it onto the hardware. So Lab 2 is the first lab where you start actually programming the physical device. Okay? So just keep that in mind while you get set up. And there's some instructions there. I'll talk about a little bit later about how to program the device and so on. Okay, I think I'm going to release this on a weekly basis. You can see the lecture notes there. The other ones I'm still going through, and the tutorial content here. And let's grab that. So it should start next week, as I said. And this particular one is Shoots Workshops, whatever you want to call it. This particular one guides you through how to use Atmel Studio. So if you've never used it before, and most of you won't have, it actually steps you through bit by bit the sorts of screens you should see. It's got some code, got some samples and so on, okay? Grab a copy of that if you want to read it over the weekend. Certainly worthwhile doing. And the direct link for the tool that you need to download there, okay? What I will say, for both the labs and both the labs and the tutes, read the labs before going in, because they're about, as you saw, about 6 to 10 pages each. By the time you read 6 to 10 pages of content, you're not going to have time to actually do the work. Okay, so just read it all in advance. Any questions about Canvas? I think we've sort of covered it well and truly enough. Everyone happy? Okay, let's get to the content. So, as I said, there's going to be 2 software tools we're going to use. We're using Atmel Studio 7. That gives us both the ability to write our code, both in C and assembler. And we're going to use a different tool, or a plug-in for it, called AVR Dude. An AVR Dude is a little application that communicates with your USB board that allows you to put the software that you create in Atmel Studio onto the board. Okay, it loads it on for us. And there's details in the Lab 2 guide on how to do that, how to install AVR Dude. And I'll try and go through it in the lectures as well so you can see where all that is. So this is what the tool looks like. It looks very much like Visual Studio. It's actually built on Visual Studio. And it has the same sorts of features as Visual Studio. How many people haven't used Visual Studio before in my follow-on course? Sorry, my previous course. A couple. Okay, cool. So most people have used it. If you're having any issues, just come and see me. We can go through it. But it's built on Visual Studio, which makes it a bit easier. Okay? Now, here's the details on AVR Dude. Now, one of the issues that we have, and we came across this last year, is for Windows 10 machines, you have to turn off driver signing. Okay? If it's on, the driver won't install correctly. And there's some details up on Canvas, I should have said. Where did I put it? Course software? Yeah, under course software, there's the actual drivers that you need to get the OUSB to be recognised when you're putting it in program mode. And it actually talks about, there's a link here about how to turn off driver signing to get the driver to install. Okay? If you're still stuck on a Windows 10 box, come and see me in the help session and we'll force the machine to do it. Okay? Not a problem. But we start doing that in about week 4. Except don't bring your desktop in. Bring your laptop in. So that's the details there to allow us to actually program that for you. Now, all of those tools should be installed in the labs and the tute rooms. If there's any issues, let your tutor know, let me know, and I'll get ITS onto it. Okay, we'll do a couple of slides and we'll take a short break. So, while you're at RMIT, while you're a professional engineer, actually, let's go back. In this class, we've got engineers, or soon-to-be engineers from many different disciplines. We got anyone from biomed? No? Mechatronics? Yep. I was going to say mainstream engineering, but it's not. Electrical, electronic, computer networks, electrical. Okay, so majority are from there. Okay. Any other disciplines? No? Excellent. Okay. Well, I guess as an engineer, doesn't matter which discipline you're from, you're going to be exposed to many different computing architectures in your time. Even as an electrical engineer, you're going to be working with these sorts of embedded systems. Okay? Now, we're all used to a standard PC. Okay, we all pretty much know how it works, how it behaves. But this is what we call this is what we call a microprocessor that lives in this particular machine. And there's a difference between microprocessors and microcontrollers. Our little USB board, okay, is what we call a microcontroller. Now, the main difference between the two is we take our computer like this, okay? It has its main CPU in it, so, you know, this one's got an Intel i7 in it. But that by itself doesn't work. Okay, if I just apply power to the processor by itself, it won't do anything. It doesn't know what to do. It needs all of these other support devices. It needs external memory. It needs something to load software from, somewhere to load Windows. It needs somewhere communicating out to a keyboard. It's got some timers. It's got USB ports and so on. So a microprocessor, like that machine, needs all of this support hardware. Okay, it just doesn't magically turn on and work. Your phone's the same. Okay, these run on ARM. Some ARMs will start up without any other. I've got an example here. Will start up without external support, but the ARM that's in here, it needs all the other chips that are on the circuit board to actually make it work. Okay, this is an old iPhone 6. They all need external support. The difference for a microcontroller, which is what we're using today, is this is a single chip solution. Inside that AVR chip, that AVR microcontroller, it's got its own CPU, so the brains that does all the work, but it's got its own RAM, so room for temporary storage. It's got ROM, which is where it stores programs, what it has to do. It has what we call I/O, or input-output. So it has things like our input-output is like our LEDs to turn on our various light-emitting diodes we might have, or to read values from the switch. It's got an analog to digital converter, timers, and so on. So the difference is a microcontroller, which is what most of you are going to use as engineers, is a single chip solution to the problem. Now, you know, I don't mind, you know, which side you're on, whether you're a PS4 or an Xbox person. Same deal with that. Okay, it just won't work by itself. All right, you need all this additional support hardware. Now, in those architectures, in our microprocessor system, we need to connect all these various things together. And the way that we do that is a concept we call a data bus. Or a bus, sorry. Generally we have two. We have data, which is the information we're storing, and then we have an address. So think of the addresses, like I've said this in Computing 1, think of the addresses are like mailboxes, individual mailboxes. At a particular address, you've got some data that you're storing in there, okay? That's how these things work, so you need these buses. Now, well, what's a bus? What's all this terminology? The idea behind a bus is just think of it as a bundle of wires, okay? That's all a bus is. It's a bundle of wires that send signals down that wire, and hopefully they arrive at the other end all at the same time. When you're working on really, really fast stuff, and I've got some examples here, if anyone had a look at their computer motherboard and see you've got circuit board traces are like little S's on the board, that's to delay the signal so that trace is actually the same length as another trace routed through the board. That's what that's designed for. So as things get faster, we need to be concerned about the length of these buses or the length of these wires. We're not overly worried about it now, but just know that we need to depend on that. And the bus width, how many bits, how many zeros and ones that represent that bus, depends on the architecture. This AVR, this little processor, is what we call an 8-bit architecture. That means that internally, all the buses, we'll say for the moment, are 8 bits wide, 8 zeros and ones, okay? That machine, that's a 64-bit i7, the buses are 64-bit wide. So there's a lot more electrical connections on something like that, okay? But that's the main difference between the two. And as engineers, you're going to be primarily faced with these sorts of systems everywhere, okay? You can't escape them. Phones got them, lights have got them. Most electronic devices these days run on some sort of microcontroller or microprocessor, Okay? It's like software. It's everywhere. Now, excuse me. I guess what we've got with these sorts of things is these are what we call a general purpose architecture. So they sort of do everything. Okay? Think about your PC. You install different software on it. It does everything you want it to do. Okay? It'll add numbers together. It might take a bit longer than a dedicated processor to do it, but they're general purpose. Now, our general purpose machines, like our PC, as I said, they take a lot more configuration to get them to work. There's a lot more setup that we need to do. Requires a lot more specialised knowledge. But you got your PC sitting here. Let's do this. Okay. So this is a 4-core i7 with hyper-threading, running at some stupid speed, 3 gig, okay, running a PowerPoint presentation at 3 gig for some reason. So that clock is running at 3 million cycles per second. But what do you notice about the machine? Well, what it does is it appears to be running multiple things at once. It looks like it's doing, and this machine actually can. It's got four main processors. So it can run 4 applications or 4 bits and pieces at once. If I've got more open than that, what it will do is it will shift them around. It says, okay, Excel, you can run on the processor core for 30 milliseconds, and I'm going to take you off, and then I'm going to put Word on so you can do it, and so on. It's called task switching. And we can actually do that with these sorts of architectures. Now, the problem with that's what your phone's doing, actually, by the way. It's task switching between all the various things it needs to do. The problem with that is it looks like it's running multiple things at any given time, but the trade-off is it's insanely complicated. Okay, that's a 4th-year course called Real-Time Operating Systems. We don't want to deal with that. We're going to deal with something really simple, or relatively simple, sorry, our little microcontroller, which can only do one thing at once. Okay? Makes our program, or what we have to write for this, a lot simpler. What do you think one of the benefits are of something that it's only doing one thing at a time? From a debug point of view, what do you think? I'm sorry? It can do it quickly. It's dedicated to that task, yep. But if it's only doing one thing at a time, you can trace it very easily. If something goes wrong, you can work out where it's misbehaving. PC like that, something goes wrong, very hard to work out what piece of software, what line caused the issue. Now, our little micro here, it's, what's this guy? Is it 40 pin? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 40 pins, okay, 40 little legs that it's got there. Does everyone know the numbering scheme on these? Has anyone ever looked at the numbering scheme on these? We do need to know this, so let's quickly have a look. Or not. No, it's going to work. Cool. This is going to be a bit tricky under the dock cam. And then I promise we'll have a short break, okay? When you look at this device, oh, maybe. Come on, you can do it. Focus. Okay, when you look at this device, see this cutout at the top? See how there's the half semicircle sitting up there? Hang on, a semicircle, not half a semicircle. A semicircle sitting there, okay? The pin, and there's a little divot there, okay? It's a bit hard to see under the camera. But that is what we call pin 1. So pin 1 is this first left-hand corner, and it goes pin 1, pin 2, 3, 4, all the way down to 20 on the bottom corner. Flips over to this side, 21, 22, all the way through to 40 on the top corner here. Really important to know, because when you plug other things into it, if you get the pin ordering around the wrong way, guess what happens? The magic blue smoke comes out and the chip blows up. Okay, so we've got to plug things in the right way. We'll do more on that as we go through. But why is that important? Well, the reason that's important is for our little processor here, for our little microcontroller, all it needs to run, all it needs to do something is we give it power, so 5 volts or 3.3, and a ground. That's all it needs. 2 pins. that device will start up and will start working. Okay? Very, very simple. This thing, it might have 25, 30 power pins you need to connect before we'll even think about starting. Okay? And then you need all the external RAM and ROM and flash and whatever. Okay? They're a lot more complicated. So our little microcontroller only needs 5 volts in ground or 3.3 volts in ground to work. All of our I/O, so all of our inputs and outputs are all on the same chip, but it runs at a much, much lower speed. This particular guy runs at 12 megahertz, 12 million instructions per second. Each instruction is 1 clock cycle. We'll get into that a little bit later. So in comparison to this thing running at 3 gig, 3,000 megahertz, it's a lot slower. Okay, but you can do so much with these things. All right. One of the big problems we're facing in the software field is, what we call, anyone heard of the term bloatware before? You end up with all this software, hundreds and hundreds of megabytes of code to do something like turn a light on. You don't need that sort of stuff. So these things are getting bogged down with doing, running things they don't need to. I can turn a light on in about 4 instructions in my little AVR here, which is very, very quick. Let's take a 5-minute break, and then we'll continue with some more of the technology. Okay, let's continue on. If the coat rustles too much on the mic, just let me know. Yeah, so I guess what we're trying to say is our embedded system, our little microcontroller that we're going to use, is a lot more simple than our standard PC architecture that we're faced with every day. Now, why do we use a microcontroller? What's the benefit of that? Why would we pick that over a PC? Well, size is obviously one thing, okay? But they're a lot cheaper. We take our little embedded piece of hardware here, and for me to go and buy one of these, for me to jump onto a DigiKey or Element 14 or any of those sorts of places, these are on the order of about $5 a chip, okay? And they're complete. And for most cases, they'll do absolutely everything you want them to do, okay? You might think, oh, 12 megahertz, it's so slow, but you'd be surprised what you can do with that many clock cycles, okay? You don't need the power of this sort of thing to solve a lot of engineering problems. Okay, it's very, very, very simple to do. Power is another thing. The slower something runs, generally the less power it consumes. Okay, and why is power important? Who's sick of charging their phone every single night? Okay, right. So if you can make something run, the clock speed is slower, but do exactly what you want it to do, you're saving power, you're making it easier for the consumer, whomever they may be. Now, it does, as I said, it doesn't matter which discipline you're coming from. You've got to understand both hardware and the software aspects of them. Okay, hardware is the physical device. It's the silicon. It's what the chip's built on. Software is what runs internally. It's the ethereal stuff we can't see. Now, anything these days that runs on some form of electricity has generally got a microcontroller on it. Sorry, I use the shortcut terms these days. Think about what you've got on. Think about what devices you're carrying today. What have you got? You've got phones, laptops, Mikey, credit card, smartwatch, even the old analog watch. Sorry, not analog. Even some watches have got micros in them. That's what you're working with. That's what you're carrying around today. And what you've got is all of these different processors doing different things. Okay? So, and it's not uncommon for something like my phone to have, it might have 10 different CPUs in it doing various different things. It might have the main ARM core doing something. It might have the baseband processor. It might have the RF front end, the camera, and so on and so forth. So, as embedded systems engineers, we need to be able to work with all of these various bits and pieces. And something like your phone, for example, when you think about it, what do we know about users? What's your reaction time of a human? Maybe, how fast can you button mash your PlayStation controller? Maybe 20 times a second. Okay. In comparison to a machine running at 3 gigahertz, well, the PlayStation doesn't, but in comparison to running a machine running at those speeds, it's an eternity. So what you often find is these very high performance systems have got your really fast processor, and then it's got a separate, what we call a slave processor, that's dealing with the user input, okay, and then passes that on to our main processor. But that's a bit more on the architecture. So, embedded systems, what choices have we got? How many people have used Arduino before? Okay, excellent. In sort of high school or on your own accord? Or here?
Yes.
Here, okay, so mechatronics people would have used Arduino before. Okay, excellent. So that's one sort of platform, and the Arduino platform is very similar to what we're actually using today, okay, or what we will be using throughout this course. But there's all these different choices, and as embedded systems engineers, you need to decide what's appropriate for your given project. So some of the common ones that we see there, we've got Atmel, which is the company that make the chip, or it's actually Microchip now, but they're still calling themselves Atmel. They create the AVR series, which is what you find in your Arduino style platforms, the entry-level ones. There's also, anyone heard of PIC processors? No, PIC's an older one. Still around. That's Microchip's main. It's funny. PIC and AVR, PIC and Atmel, were separate companies. Atmel was destroying them with the Arduino platform. So what did Microchip do? Bought Atmel. Okay, so now they run it. ST Microelectronics is another one. So I have... Anyone heard of an ARM processor before? Yep. So here's an example. This is an example of an ARM. This is actually built by one of your fellow students in their capstone project. If it loads. Cool. It's a bit hard to see, but you can just see the words ARM on the top. Okay, and that's made by ST Microelectronics. So that's that little ARM, in my car, that'll do. That gives you context. Okay? It's not that big, all right? That runs at 168 megahertz, 168 million instructions per second. And then, that same chip, that's called a leaded chip. You can see it's got all the little leads that come off it. No, you can't. You can see all the little leads that come off it that you can solder to. And if you want to make things really small, same processor. This is what we call a BGA device. This is made by a company called emb.syst. Systems. You can see it's got ARM written on it there. Now, it's tiny. Okay? 168 meg, it's got 32 meg of flash and something like 32 meg of program code and 64 meg of RAM all on that one little chip. Okay, so as embedded engineers, you've got a lot of choices. But one of your major choices is which board do I pick and why? Okay, and you need to decide that. This guy, as I said, the main core is about $5. This one, to create that package there, that board cost me $200. Okay, so you've got to make a decision. Why would you pick one thing over another? To control something like a light switch, you don't need 168 million instructions per second. Okay, you don't need the processing power of an ARM. You can get away with something like the AVR. Okay, so that's what you're going to find when you're making these sorts of decisions. Okay, some of the other platforms that we see these days, got the MCraft board, that's fine. Anyone heard of the Raspberry Pi? That's one of the older ones. Okay, quite common as well. I think they're running at 1.2 gigahertz these days, and they'll run a Linux distribution. So they call them a little single board computer. And so these are all aimed at different markets. You know, for this guy, for the main core, $5. This one's about $18. And unless you buy hundreds of thousands or tens of thousands, you can't even get this processor core. I can't get it as an academic. I can't even get the data sheets on how it works internally. Okay? So if I'm making 100,000 units of something or 200,000 units of something, okay, which one am I going to pick? I'm going to try and pick the cheapest processor that's going to do the job for me. And that's part of your decision process, okay, when you're working with embedded systems. But that's some of the common ones that are out there. So our OUSB I/O, that's our target that we're going to be using. As I said, I've spoken about, you can use one from last year, not a problem. If you're running, one of the comments I had during the break, if you're running in 2246 and 56, you can use the same board in both courses. You just have to reprogram it. Okay, it's not a big deal. And I can show you how to do that. There's not a problem. Now, last year, when we were using this, what did we do? We used the OUSB.exe to communicate to and from the board, didn't we? And so what we were doing was sending commands over the serial port, weren't we? Yep, and our board was interpreting and doing something with it. This year, all that goes. What we're doing this year is we're writing code that runs on our processor itself. Okay, it's not communicating to the outside world at the moment. Doesn't. The only reason we run it over USB in this semester is to power it and to program it. Okay, it doesn't behave as an OUSB board like you had last year. So, in 2246 or the earlier 2250 in some of those courses, what we had actually done is we'd written software or firmware on that board that controlled the LEDs when you sent it commands, that did stuff like that. Okay, so that's the difference. You're now writing that code. And as I said, there's class sets and so on if you don't want to buy your own. So now, how do we select a processor? What do we actually decide? What was the decision? And why this processor, I guess you could say, and what are the restrictions? When we write code, when we write C code, and we're going to do that later in the semester, we know that when we write C, it's designed for a specific architecture. So if I compile something in Visual Studio on my computer here, and you're running Windows and an Intel-based PC, you can run that same piece of code, right? But I can't take that compiled code and run it on any of these boards. It won't work, okay? C is target specific. It has to be for this particular application. So that also means that the requirements change. You know, how big can my code be? How much data can I fit into it? This thing's got 16 gig of RAM and runs at 3 gig, okay? And it's got a 500 gig SSD in it, I think. This guy, our little OUSB board that we're dealing with, or our little AVR, actually I should mention, C's got ATmega32A, that's the actual chip. That's the main controller. So throughout the lecture series, I'll probably call it an AVR, but I mean that chip, all right? Our little chip that we're going to be using has only got 32 kilobytes, 32,000 bytes of memory, of program code. That's it. That's got 500 gigabytes. Massive difference, okay? It'll run at 16 million instructions. We're running it at 12. But in terms of RAM, in terms of temporary storage, it's only got 2,048 bytes. You can only store 2,048 values between 0 and 255 in that processor. That's it. No more. Okay? So there's very, very tight constraints. And when we're writing our code, we have to keep that under consideration. Because if you said, oh, I want to use a megabyte of RAM or 2 megabytes of RAM, you don't have that. It's just not there. Okay? Even on the ARMs, even on this one that was worth $200, is 192 kilobytes. That's it. Okay? Unless I use the external stuff, which is a whole other ballgame. So when we're writing code for these architectures, for these systems, we have to be very, very careful. We have to write our code accordingly. Does anyone ever know what non-volatile memory means? What's the difference between volatile and non-volatile? What do we think? Yep.
Non-volatile doesn't degrade when powered down.
Exactly. So when we write software for our OUSB board, when we write the firmware that sits on this, we flash it, we program it, we unplug it, we can go and put the board away, and we plug it back in, power it up, that same code will still be there. It retains the code. It means it's non-volatile. Volatile means as soon as you unplug the power, it loses whatever's going on. Okay? And that's one of the benefits of these. Imagine having, you know, your light switch, your iron, whatever you got, and have to reprogram it every time you want to use it. It's not going to work. Okay? You're not going to buy that product. So it has non-volatile memory in it. What else is interesting? Voltage range. These run from 2.7 to 5.5 volts. Okay? We're running it at 5. These ARM boards, this one, 3.3. If you put any more than 3.3, you blow it up. Okay, so we certainly don't want to be doing that with either of those boards. It's 40. I mean, it must have miscounted. 44 pins, it says. It might be a different variant. But it's got some communication interfaces, which we're going to actually talk about all of these throughout the semester as well. Okay, so that's our little processor. And if you want the data sheets, if you don't want to grab them from Canvas, you can certainly grab the data sheets from there for our device. There's the link to the data sheets. An important, really important part of this is actually being able to interpret those data sheets. So let's very quickly. So this is a copy of them. The three that you need, the instruction set manual, the data sheet, and the data sheet summary. These tell you what the device is, all the bits inside it. We're going to go through this in detail. The pins, so what's connected to what pin. It was a 40-pin device and so on. There's the full data sheet. So the summary was 22 pages. This one's 414. Goes into a lot more detail how it works internally. And the last one at the moment that you need is the instruction set manual. These tell you what instructions, what code our little processor is going to understand. And in the case of this processor, there's only 131 instructions, that's it. Okay? So within reason, they're fairly easy to memorize. 131 is not too bad. I don't expect you to memorize them. You just got to know the family. I'll explain that a bit later. You just got to know what you're really looking for as far as that's concerned. This guy, the assembler level instructions, the instruction set reference is about this thick. Okay, it's about I think it's 2 manuals of about 900 pages each. Okay, I'm not going to memorize those. So they're the data sheets that you need, and part of this course is going to be actually looking at those data sheets and interpreting them. Now, in terms of architecture, what's inside this chip? What are we really concerned about? Because we said it's a microcontroller, what it's got is it's got its CPU up the top, AVR CPU, and then it has this data bus. See this big bus here? And that transmits or transfers information to all these other little sub-blocks inside. So sort of week by week, we're going to break down each one of these sub-blocks and explain how it works. Okay? So we've got our main CPU at the top. We've got our RAM, SRAM, our program memory, which we call flash. We've got our inputs and outputs called I/O ports. ADC is analog to digital converter. Comparator we're not going to cover. This is called I2C or two-wire interface. This is a serial port. So this is a really easy way of transmitting data back to a computer. This is a thing called serial peripheral interface, and so on and so forth. So there's a lot of little blocks that we're going to be covering throughout. And the benefit of this is that this is an AVR, that's fine, but the way that these work and the same sort of processes can be, not processors can be applied to different architectures. So once you understand how the serial port works, here, I can apply that same sort of knowledge in getting the serial port on my ARM processor to work. Okay, so it's sort of universal. Initially, what we're going to be considering is the part to deal with the I/O ports. Okay, so what I recommend you do is grab a copy of the reference manuals, as I've indicated. It's the ISR. Which one's that one? This is the full data sheet, and you'll see here that there's a section on I/O ports. Okay, so you can start having a flick through it. You're not going to understand it yet, but you can at least see what it works. And we'll go through how it works. We'll at least see some of this in detail as we go through the semester. Cool. So the first part that I want to talk about, is this CPU. And we're going to go into a lot more detail next week. This is sort of the introductory part. Now, inside that CPU, the central processing unit, there's a lot of little things we need to consider to make this thing work. And this is the internal structure of what you see here. We have a thing called a status register, which tells us what the CPU is doing. Okay? We have an ALU. Anyone know what an ALU is? It's an arithmetic logic unit. So this is where the math happens. We have some registers. These are like temporary storage blocks. Okay? There's 32 in the case of this little processor. We have some RAM. We have some special things at the top called a stack pointer and a program counter. A program counter tells us where we are in our program. What line are we running? We run that line, we increment the program counter, we go to the next thing. We run the next line and so on. We have some instruction registers and some instruction decoders. We'll talk about those a little bit later. We have control lines. So in a summary, what really happens is we put our software in here, we put our firmware that we're going to write in AVR Studio into here, and everyone heard of a state machine before? 2251, okay? Our state machine takes that instruction, decodes it, and says, oh, processor, you need to do this now. And it runs those instructions, gives you the results. Then it just goes to the next instruction, does the same thing, decodes it, runs the operation, saves off the result, okay? That's how most microcontrollers work. So internally, there are 26 general purpose registers, which are 8-bit, and then there's 6 that are designed for specific operations. Now, this is what we call a Harvard architecture. That means that program and user data are separate. See, we've got program information here and user data sitting out over here. That'll become more important as we go through. We have these general purpose registers, which are the 26, and then we have some specialist ones called X, Y, and Z, and we can do certain things with those. Okay, and so on. Now, the fundamental building block of all of these is what we call a register. Okay? Within every micro that I've come up with, that I've come against, they all start with registers. They all have registers in them. And you can think of a register as a collection of bits, zeros and ones. Okay? So that register normally can be an 8-bit register, a 16-bit register, or a 32-bit register. That means it has 8 zeros and ones in if it's 8-bit, 16 if it's 16-bit, and so on. Okay? Everyone follow me so far? Yep. Anyone? Okay. So binary, let's go back to binary. A bit is a single unit of information. It's either a logic 1, which means, for example, switch on, or a logic 0, which means switch off. Everyone's covered that before in some other course? Yeah? Okay, good. So we have a register that contains our 8 bits, 8 zeros and ones. Now, if it's 8-bit, how many values can we store in that register? What's the minimum and maximum values? How do we work that out? 2 to the power 8, so 0 to 255. 256 values, but 0 to 255. Okay, so our 8-bit register, the largest number it can store is 255. 16-bit register, how good's your mental arithmetic? 0 to 65535, I think. As an embedded engineer, you get used to the numbers, I tell you. Don't ask me 32-bit, it's like 4 billion, something along those lines. So we store these zeros and ones. Now, how do we create these registers? What are they really? Now, what it comes down to, we can think of these individual bits as what we call a D-type flip-flop. Now, PJ would have gone through that in Design 1, is that correct? Yep, and we use them in our state machines. We use them to store 1 bit of information, didn't we? Yep, a D-type can store 1 bit of information. If you're not sure about this, let me know, and I'll provide some other notes, there's no problems, and there's some actual revision on this on Canvas. So here's my D-type flip-flop. Now this is, this one's a little more advanced than usual, but what do we have? Well, we have D is our data input, Q is our data output, we have an enable signal, we have a clock, we have a reset, a preset, and QN. What do the circles mean? Active low. So if we have a 0 here, it means that our reset's active. If we have a 1 here, it means our reset's inactive. Same deal with the preset. At the moment, I'm not concerned about those. Let's ignore those reset and preset signals. Clock. Now, what does a clock do? Well, our clock goes from logic 0 to logic 1, then back down to logic 0, and back up to logic 1. So it generates a square wave. And the way our D-type flip-flop works is if enable is high, if this is high, every time we get a rising edge clock pulse, data is transferred from D to Q. Okay? And if we don't get a clock pulse, whatever used to be on Q stays on Q. Okay? It holds that bit. Now, you can see from the truth table, this is really what's actually happening. Okay? Now, everyone comfortable with reading these? Yeah? All right. What do we have? Reset and preset. Now, I said we're going to ignore those, so how do we ignore those? We only look at the entries that have 1s in it, because if it's a 0, it's active, so let's throw them out. So, only interested in the ones with 1s. What does this indicate? Rising edge clock. So this means that when our clock goes from 0 to 1, something happens. Nothing happens when it goes from 1 back down to 0. It's a rising edge clock. Cool. What are the X's? Don't cares. Exactly. We don't care what it means. So when we read this, what do we say? Well, let's look at the load state, which is this one. If data is 0, our enable is high, and we clock it, Q goes to 0, and QN is the complement of that. Okay? So Q and QN are always inverted from each other. All right? Equally, if our data is 1, our enable is 1, our data is 1, and we clock it, our output changes. Okay? Now, you never, ever, ever gate a clock. The clock goes to everything. So if we want to load something into this, one way we can do it is we can control the enable. All right? So remember, back here, we said there's all these control lines. Yep, this part. Those control lines go to this enable. And so by those combination of those control lines, it allows us to take something, store it in that register. The enable goes off, it stays there. Okay? That's how these sorts of things work. So, now, the question is, do you believe me? No? Well, I've got a timing diagram. I actually generated this in another tool we use in fourth year called Cordis. Here is the actual waveform, and you've got to be able to interpret these. Okay? What am I actually looking at? Well, I've taken out reset and preset. Enable clock D and Q. All right. Here's data. Here's Q. Enable is low. So my clock's coming along, doing what it should. It just keeps doing its thing. And I get something on data go high. Okay? I get my clock going high, but why didn't Q change? Q's is still at 0. Is that right? Yes, because the enable is low. Okay? Cool. I now change my enable, all right, and here's my clock. My data is high on the rising edge of the clock. What happens? Latches through, goes to Q. Okay? And what else did I do? Oh, yep. Data went to 0 here, and on the next rising edge of the clock, my Q dropped to 0. So this is what we call a functional diagram or a functional simulation. It shows functionally how this should work. Now, what have you noticed about Q in comparison to clock? What has it done? Well, my data transition was only this wide, but it's taken this long to go back down through 0. 1 through to 0. Why? Exactly. So every rising edge, something happens. So I've halved the clock speed, haven't I? By doing that. All right. So we need to be careful where we use these. What else do you notice about the alignment between the clock and data? What are we seeing? They're not on the same edge, are they? Do you think I've done that deliberately? Okay. These devices, go here, this is an enable one, so this is enabled. The data must be present before the rising edge, because if it's not, it misses it, right? It only clocks through on the rising edge. So there's a minimum amount of time, called the setup time, from here to here, and this might be like, 5 nanoseconds, but there's a minimum amount of time that data must be present before clocking it through. Okay, and so this constrains how fast we can run this processor. So that's effectively the D-type. So we're storing 1 bit of information, okay? And that works, doesn't it? Everyone's happy with that? Okay. So moving on, I did this Wednesday night? Yeah, Wednesday night. This is in Cordis, and what I've done is I've said, okay, that was a 1-bit register. Now I want to create my 8-bit register, so how do I do it? Well, I've got all of my D-types, 5, 6, 7, 8 D-types. What have I done? I've got a common clock, so CLK goes to each one, all right, and a common enable, right? And what I've done here is, this is an 8-bit wide data bus, 7 to 0. I know it's really blurry on the projector, but that's data coming in, 8 bits wide. And I've got data going out, Q, which is 8-bit wide as well. And this is flip-flop for data bit 7, data bit 6, 5, 4, 3, 2, 1, data bit 0. Okay? There's my 8-bit register. It's nothing more than 8 D-type flip-flops stuck together with a common clock and a common enable. Okay? And so all my buses, remember we said we had a bus, 8 individual wires. So there's one wire going in there, and another one going in there, and so on and so forth. Okay? Now your CPU might have thousands of these registers, but this is effectively how they work. This is an 8-bit, which is like the AVR that we're using. You can do 32-bit, it's not a problem. We run the simulation, and this is what we get. Now, I'm not going to sit and decode all of this, but you can see that what we've got is enable and clock, which is here and here. So there's my enable. It's not doing anything. My data's changing, okay, here and here and here. It's definitely going through on the rising edge of the clock, but because that enable's low, it doesn't latch to the output queue. It doesn't follow through. But as soon as we toggle that enable, my data latches through to my output. Now, what's the problem with this diagram? It's hideous to read, isn't it? It's really hard to work out what's going on. What you can do is, we normally I've just exploded this out for each individual bit. So this is bit 7 through to bit 0 for the output Q, and then D, bit 7 through to bit 0 for the D. You normally display this in hexadecimal. Okay, so you don't have all this binary stuff going around to see what's going on, because it is really, really tricky to read. There was something else I did weird on this one. Oh yeah, down here. What do you notice about this time index here? What's strange about that one? Well, we've missed something, haven't we? But what's going on here? We've got high, high, high. What happened to D? When did D drop? On the clock edge. So we have to be really, really careful with timing. Okay? Because the simulator's gone, oh, the two things are aligned, it must clock through. But what do we know? There's a setup time that we need. So that's an example of a simulation giving you garbage information that may or may not work in reality. And, believe it or not, if you design some silicon to do that, and you can do that in my 4th year course called Advanced Digital Design, we take that. And if we had a piece of silicon like that, we could have it sitting on the bench and it could work. Okay? Put a hairdryer on it, heat the chip up, and it may not work. So the timing constraints change depending on temperature as well. So that is a really, really nasty thing to do. You have to watch that. That data's got to be there for the setup time, otherwise it won't work. Now, that's all good. So we've got these things called registers. Everyone following so far? Yep, we've got these registers. Well, how do we use them? What's important? And the first important one is we call the status register. And you can see this is here in figure 16. If you jump into here, I think this one, jump under CPU core, status register, that's where that information came from. And this register tells you what the CPU is doing. These are what we call flags, or individual bits that say, hey, this condition's occurred. So whatever your last instruction was, it's caused this to happen. So when we look at this, what have we got? Well, we've got what we call a carry bit, so bit 0. So the way we order these, bit 0 through to bit 7. Bit 7 is the most significant bit in this architecture. Bit 0 is least significant bit. So that means the bit number. The RW means whether you can read or write to that bit. And when you reset the micro, that's its default value, is how you read this slide. And these bits mean certain things. So this is called the carry bit. Okay? This is the 0 flag, the negative flag. We use them, and there's a couple of other ones, eyes interrupt down the end, and so on. So the CPU, the AVR, makes decisions based on these flags. This is how the instruction set actually works. So think about 2246, computing 1. You've got an if statement. How do you think an if statement actually works? How do you say if this equals that? What are you actually checking for? What mathematical operation could you use to do that? Equals, yeah. So you could check if it was equals or not equal. What if you subtract one from the other? Yeah, exactly. So if you subtract 10 from 10, does 10 equal 10? 10 minus 10, what does it give you? 0. What flag should get set then? The 0 flag, bit 1. Okay? So things like those statements that we've seen before, things like if statements, like case statements and so on, they map to the actual architecture. If we want to check, does something equal something? 0 flag. Less than or greater to, you've got a negative flag. One number minus the other. Branch if negative set, branch if negative not set. Okay? We'll discuss the branch thing in a minute, or maybe next lecture. But these flags are what controls your CPU. It's no different on my laptop than it is on the CPU architecture. On the AVR architecture. It uses these flags to do certain things. Okay? Which is really cool. So, firmware, writing firmware. Now, these things have got a heap of peripherals in it, all sorts of good stuff. But the problem you have is when working with embedded hardware, one of the problems you've got is that they're really, really tricky to debug unless you develop a really good set of processes to actually physically try and work stuff out. The problem you have with a micro is they're often in mission-critical environments. Okay, they might be in your traction control for your car or safety systems for elevators or trains or whatever you're trying to do. So you have to be very, very careful when writing code for these things because you can make them crash. And when you've got a board like the OUSB and any of these ARM boards, if they crash, it's very hard to actually work out, well, what's gone wrong? Why did it crash? I can't, at the moment, peek into that and see what's happening. So we have to be very careful when writing our code. For high reliability designs in automotive, we use a thing called a real-time operating system, and it protects a lot of this sort of stuff. But you can do that with Samuel up in 4th year if you decide to take this path. Now, when we write code for these things, traditionally we use what we call assembler. Has anyone heard of assembler before? Okay. What's assembler? Assembler is, I guess you could think of one layer away from the CPU. So assembler is what you see in the instruction set manual. Okay, this particular one here. You can see there's a bit of info about the flags that we spoke about. But assembler, these are mnemonics or terms, if you like, or 3 or 4 letter little descriptions that represent an instruction we want to do. So let's just say we want to add 2 numbers together. This is it here. This is add with carry. It doesn't matter. Just add. Okay? So what happens is assembler, we say, is one level away from the actual CPU core. We can take our assembler instruction, add with carry, and we can actually represent it in binary, in zeros and ones. Okay? What does the CPU understand? It only understands zeros and ones. Okay? So these assembler instructions are one layer off the machine code. Would you write in machine code? I'm not going to do it. Okay? But you certainly could if you wanted to. Now we take C. What do you think C does now? C, you take your C code. Effectively, you can think of it being converted to assembler. Goes from assembler down to machine code. Zeros and ones. So that's the entire path of how the thing works, or sort of. Okay, so that's the idea behind it. So for assembler, we use these 3 or 4 letter mnemonics, and you can see them all there to represent a certain operation. So this particular one is add with carry. Okay, and we'll go into what how we do it in a second if we get a little bit of time. Now, one of the problems with that is in 8-bit systems like the AVR, they're manufacturer specific. So if I want to learn assembler, and I do know assembler for a few micros, the instructions for this AVR are the same, generally similar to most AVRs, but the assembler level instructions for this one is very different to my ARM processors. The same instructions don't work. So if I want to code in assembler, I have to memorize or know the instruction set for each specific machine, okay? Which is why we only do it for 1 lab or 1.5 labs, okay? Because memorizing them all for every architecture is very, very challenging. One of the benefits, though, of assembler is we can absolutely control everything the CPU does. We can see what instruction's running, how long it's going to take before it moves on to the next thing. With C, you can't see that. You just press compile, it does something, and you hope that it works. So that's why we'll start with assembler because it's a bit easier for these sorts of things, and then we'll go up to C. Now, there is a push in industry for ARM code. So these are what we both call ARM Cortex M4s, made by ST Microelectronics. In the ARM arena, there's another company called NXP. I can take assembler code that runs on these and run it on an NXP machine. So they're trying to make that standardized. But in terms of the 8-bit processors like the ABR, it's not standardized yet. Okay, now, we'll see how we go. If not, we'll finish it up next week. So our little processor, our little ABR, has only 131 instructions. That's all it knows how to do. And they're in that instruction set reference that you can see. Now, this is what we call a RISC architecture, a reduced instruction set computing architecture. So minimal amount of instructions, but they run very, very quickly. These older machines, not this one, but other machines used to be what we call a CISC processor, complex instruction set. The original Pentium series with things like that. More instructions, but they took longer to run, so that's the trade-off. The instruction to code, how it decides what to do in a RISC, is done in the silicon. In a CISC processor, generally there's another piece of software that you can't get to that's interpreting the instructions. That's sort of the difference between the two. But this assembler is, we'll call it human readable, okay, and then mnemonics that we can understand. When we put the code and compile into AVR Studio, it takes those assembler instructions and converts it to machine code, the zeros and ones that the actual CPU can understand. Okay? And the beauty of Atmel Studio is that we can write in C and we can write in assembler as necessary. We can actually mix the two if we really want. Yeah. So the question, well, if we can code in C, why are we using assembler? What do you think? Why would we use it? What's the benefit? I mean, what are we trying to do? We're not trying to make life difficult for ourselves. Okay, so why do you think we would use assembler? What would be one reason? Well, if you're sitting on the machine, if you're as close to the silicon as you can get, you can hand code everything. So if you want something to run very, very quickly with a predictable number of CPU cycles, okay, you can do it in assembler. It's very hard to do that in C. Because I take a C compiler, this, version 15 of the C compiler, they change it to version 16, they optimize the way that it does something, my instructions run at a different speed. Okay? So I don't want to be doing that. So certainly for, if we want to control exactly what the machine's doing, we certainly do it that in assembler. We shouldn't really do it, we can also bypass some of the error checking in C. If we want things to run really quick, we can bypass some of it, provided we check some other way. Just, we don't want errors occurring. And things like ISRs or interrupt service routines, they're often written in assembler. They're mission critical, they're time critical, okay? If you want something to fire every millisecond exactly, you do it in assembler. If you want, a millisecond this time and maybe 1.05 milliseconds the next time and maybe 0.95 milliseconds the following time, do it in C. If you need precision, we do it in assembler. And most of our CPU runs at most of the instructions run at a single clock cycle. So you get 12 million instructions per second. It's quite quick. Quite quick. In this architecture, the instructions that we're using perform operations predominantly on the CPU registers. So if you want to load something if you want to add two numbers together, generally what you have to do is take the number, put it in a register, take the next number, put it in a register, tell it to add the two registers together. That's the way this architecture works. Okay? Some other ones will let you add with RAM, so you can put a number in one of these registers, then add it to the value in RAM over there and get the result back. But typically, the instructions are register-oriented in this particular machine. Okay? And there's limits. So, for example, you can only, in this particular machine, you can only load a literal or an immediate value, a number, into register R16 through to R31. It's actually constrained in the silicon. Okay? And if you do it and you think you're putting it somewhere else, you're not going to get what you expect. Now, because we start actual coding next week. The question is, well, because you're going to have to write code next week. We haven't looked at it yet. The question is, well, how do we write assembler? You know, there's these 131 instructions. How do we pick what to do? The key to writing assembler code is write it down on paper. Write down the operations you want it to perform on a piece of paper. If I want to add two numbers together, what does my piece of paper say? Load the value 15 into register 22. Load the value 17 into register 23. Then add them together. Once I know what that's about, I can take that and go, okay, I want to load something in. I want to store something. So I come to my instruction reference and go, okay, load instructions. Load immediate. Okay, I need to use that. How do I use that? I want to add something together. How do I do that? I come up to add here and so on. So don't look at the instruction reference manual and go, where do I start with all this? Write it down on a piece of paper first. That's the key to all of that. Okay? Now, we are a little bit short on time. Patience. Patience is the key for writing assembler. Okay, it's very beneficial, but it can be a bit tricky. There's an example there. We'll go through it in a bit more detail next week. We're going to get into, we'll actually be really coding next week. This is more of an introduction to set us all up, how it's going to go. The tutorials are vitally important. It shows you how to use Atmel Studio. And remember, labs start next week, as well as the tutes. All right, I'll see everyone next Friday.
The OS for the OUSB board.
Yeah.
Basically, it's asking them to plug it into the J9 header.
Yep.
I was just wondering, like, where that is.
Just there.
Yeah. So what would we need?
So you take the jumper off there.
Yep.
And you pop it on there.
Oh, right.
And then all you do is you program it over. Yep. But I'll release the lab. I didn't realise I hadn't had it released. It actually steps you through how to do that as well.
Okay.
Yep. I'll do that for you. No problems. It's just slipped. That's all.
Yeah, sorry. I was just wondering, because in my current program structure, I have this course
Right.
running concurrently with Digital Systems Design 1.
Okay.
And I'm just wondering if that will cause any.
You'll be good. If you
Because
get,
it was mentioned in the prerequisites.
yeah, it is, but if you get stuck, come and talk to me and we can run you through. Okay? Question? Yeah, right.
Flashing the USB.
Yes.
Is that? Can you release that information?
Yeah, I'm going to do. Yeah. I didn't realise I had it time locked. I'll fix that when I get back to the office.
Awesome. Thank you very much.
Under lab 2. Okay? Yep. Cool. No problems. You doing?
Just for some clarification on the lab assessments.
Sure.
Are they assessed only every second session, or are certain tasks assessed at the end?
No,
of each
every
one?
second session
Right.
is how it works. But if you get it done in advance, have it marked off, because the marking weeks become really crazy busy.
Right.
And the sooner you can get it marked off, the better for you.
Okay, great. Thanks.
Cool.
I was wondering, when is the help session again on Friday?
Next week, 4:30 to 5:30.
Okay.
10, 9, 11.
10, 9.
Yeah, but I'm running it with another class, so it could be busy.
Computer engineering.
Computing one.
Right.
So I'll do my best to get to everybody, but
What is it again? 10,
10, 9, 11.
9, 11 at 4:30 to 5:30.
Yep, exactly.
Thanks so much.
No worries.
Do it. What's your favorite topic? I'm unenrolling out of the business class. Where you guys thinking about it?
Yeah, engineering. It seems like it won't be that bad, but I've heard assembler's a bitch from what I've seen.
Assembly is a bitch. It is. And the worst part is assembly is different for every microprocessor.
Yeah.
Like